Title of the presentation, as written here by low temperature StirLing Engines, theory and possibilities, to point it out at the beginning. Title of the presentation, as written here by low temperature StirLing Engines, theory and possibilities, to point it out at the beginning. Theory is a big word, because if I should go really into theory, it would be boring for most of you. It's a lot of thermodynamic theory, and the good thing about it is that normally you would say it's too much science, I don't understand it, must be studied people like physicists like me who can do such things, and the real world is completely different. Because I tell you the story, I start the invention of the StirLing Engine in 1812. It was an age when the first thermodynamic engine had been developed just before. It was a steam engine, which then started, as we said, the industrial age. And the first steam engines were used widely in Scotland and England to light water pumps and to pump out of the mines, salt mines. And working in the coal mines were mainly children. And because the steam vessels were under pressure for the steam engine, provisioning the steam engine to run, were built out of wood with steel rings. There were a lot of explosions happening and a lot of children killed. So Reverend StirLing was a reverend, he had a brother, he was an engineer. So he said we should invent an engine which is not running with a dangerous steam. So couldn't we build an engine running with air? But in principle it's the same system, closed container, but no water becoming steam, just air inside, which is heated from the outside and starting expanding and creating more. So they built it, and at this time no thermodynamics theory was known, not at all. Of course, you knew this was already in the first engines running with air were not built by StirLing. They were built 2,500 years ago in Mesopotamia in Egypt, and you had some priest shamans who didn't say what they did, but they had big temple doors, tons of weight, and they opened to say we are the shamans, but because they knew that there was an air container behind, and they heated it with fire, so they said we are doing wonders. And I will go a little bit more trying to describe the principles which are involved in a StirLing engine without using more than, I will use only one formula. And this formula will then is the theoretical possible efficiency of air or a gas being heated at one moment at a higher temperature, so building up a pressure, as you all know. If you have a vessel closed, filled with air, you heat it, you must take care after a certain while, boom, it will explode. And then if you have a vessel filled with air and you cool it, after a certain while you will see sucking in, pressure becomes low. So heating a gas brings high pressure gives power. If you replace in the picture I just gave in the pot, if you replace the top by a movable top, sort of a piston, if you heat the gas, it will come out and will create power to the outside, and if you cool it, it will retract and come pull it back. So if you are heating and cooling in a change in an interval, we will have a pressure fluctuation, higher pressure, lower pressure, higher pressure, which is working to the outside world. But this will be explained much more precise. The terminus for efficiency. Efficiency means how many percent of the heat introduced in the gas is transformed in mechanical energy, which then I can change into electricity, into cooling, into mechanical energy. So it is described by the temperature on the high side in Kelvin. I will explain this short. Minus temperature on the low temperature side divided by the temperature on the high temperature side. And why in Kelvin? I must explain. If you look to temperatures, we have in centigrade, 0 degrees centigrade, and then we have temperatures rising, which can rise to infinity. You can have a temperature of the sun is 5,700 degrees. But you can have other stars with temperatures of million of degrees, and there's nobody is forbidding that in a fusion reaction, when stellar systems are colliding, you get temperatures nearly endless. So you would think that on the minus scala should be the same, but it's not true. The absolute zero is minus 270 degrees centigrade. Then you cannot cool further down. To explain this, you can only give a picture. You know, if you're vulgarizing science, which normally is written in equations, you are always simplifying. But also, if you are writing down the equations and you believe you understand completely the nature, is not true. There's always something underlying people. So I'm not telling you that I explain you exactly how it functions, but giving you just a little bit indication. What is temperature? Let's take a little, could be cylindrical container of gas, air, and we introduce, I symbolize it with a flame through the wall. We heat the wall, and then we heat the inner. And what happens is that suddenly these gas molecules are moving faster in all directions. So heat is changed to kinetic energy. That's evidently what is also causing pressure. If you consider these little molecules as particles like ping pong balls, it makes a difference if this ping pong ball is played softly or with a high power. So this impulse coming on the wall is the energy we can extract. Now, if we cool it down, see if we heat it, the vector means the speed impulse in one direction going to all directions. Statistically becomes shrinks. And so, until the moment, the molecule is no longer moving. And this is the absolute zero. That's minus 273 degrees. So, this was a Frenchman, Sadi Carnot, who about 60 years after StirLing built by intuition, I will come to that, a nearly ideal engine. He described the formula. And now I ask Daniel to calculate if we would have a temperature on the high side of 100 degrees centigrade, which is in Kelvin 373 Kelvin, and if we would have on the cool side the temperature, typical temperature we have in a well in the water, because this is our cooling side, 20 degrees centigrade. Right? So, and I will produce a little scala, which is the efficiency over the temperature difference we apply to the gas. Yeah, you see. It means, and I will point out the importance of this. If we have a delta T means simply the difference between the high temperature and low temperature. We just calculated for 80 Kelvin. So if I at 80 Kelvin, which is a feasible, pragmatically feasible, everybody working a little bit in solar energy knows that it's extremely simple to reach with simple solar collectors, as we show it here, 100 degrees centigrade at a good efficiency. And everybody knows that in fact that a well has a temperature of 20 degrees. So there, between these temperature differences, we just said 21%. So maximum, nobody can go over 100% according to the classical laws of physics. Many people speaking about free energy and others, which is something completely different. But we stand here on grounds which we are completely sure. So we are at 0.21, and please now calculate, if you are in a solar system, we speak about solar energy, calculate the efficiency for the highest possible temperature we can reach with the sun. That is the surface temperature of the sun. It is 5,000. I say it's in Kelvin, or in I think 500,000, 700 Kelvin already, and calculate it again against 20. So if someone has
you think we get the full temperature?
Yeah, in principle that's just as long as you calculate. If you have a mirror, a very precise mirror, an astronomical mirror, and you are concentrating the sun to a very small spot, then the highest possible temperature is just the surface temperature of the radiator, and this is the sun. So of course we don't reach it, but have been reached in real technology over 3,000 degrees centigrade. So very high temperatures. What do we have?
95.
Huh?
95.
Yeah. Look, if now we go to the solar temperature, we are here. That means take another color. 95, nearly 100. Something like this is the function. The first thing to see, of course, everybody would like to have 95%. You have pure light, and you transform it in an engine to practically 100%. All photons transformed in energy. It's a physical possibility. But now we speak about pragmatic realization. First of all, if we are going, if we should have an engine which works at 5,700 degrees Kelvin, so first of all, we don't have the materials. It melts down. And secondly, because we don't have the materials, we can't build it. There's many, many other reasons. It is more complicated than the most complicated technology we have today. So the tendency is to say, okay, 5,700 we cannot do, but at least you can calculate one other 1,000 degrees centigrade. But maybe we could go at 1,000 delta T. 1,000 will not be too bad. Huh?
77.
It's not too bad. Huh? We're already 77%. Now pointing out. 1,000 is feasible. And we have built engines with 1,000 degrees. And of course then you need austenitic steels to all the very special alloys. And you can no longer work with air as a gas. You need helium or hydrogen. And you are running into a lot of problems of the tightness through the wall, diffusion. It runs, it's fascinating, but would never be an engine, I would say. We go to Berlin and even not to Germany, if we have not the sun, maybe we could build it. Very expensive. So we see at low temperature, easily feasible, potential already 20%. Now I want to put this into a relation. What does it mean? Is someone of you knowing what's the efficiency if you have a car? You have a car, and inside of the car you have temperatures of 1,000 degrees when you explode your fuel. So if the car engine would be built according to the thermodynamic limit laws, you should have an efficiency of 70%. 70%. Do you know how much an automotor has as efficiency? Meaning
5%.
20, correct. It's around 20. So we realize that the potential of a StirLing engine, potential, we are coming then, what can we really do? Already at a temperature, very soft temperature of 100 degrees, reaches the efficiency of engines which have been developed over 100 years with an input of billions to bring them to the stage they are. So that's interesting. So that was the base. When we were working and developing the high temperature systems, we said, okay, it's fascinating. It took us we got over 10 years of our life in high temperature engines. And we also started thinking, how can we avoid the difficulties associated with very high concentrated solar energy. And there's complete other thing. We built windows out of quartz, and we got directly with the radiation into the gas to be heated. And since the gas is transparent, it's not heating ice. So he had to produce some type of a black gas. All this works, but after a certain while you have corrosion and all these things. So one of the reasons we want to come very near to the 21% is that this is something which can really, someone said it's a game changer. It's really a game changer. If you can use solar heat in simple way to produce something in this range of efficiency, it will be a game changer. Now, what is today the perspective of reaching, we are speaking of the sun, with the solar energy efficiencies around 21%. It's evidently the photovoltaic cells. At the moment, the photovoltaic cells in market, in average, you have to look this over a year. If you look at the prospectus, they say, hey, we have a wonderful solar cell, it has 18% of efficiency. But in the average, we will be in the 15%, which is okay. If we have, if you look to a semiconductor, very nice, a plate changing with 15% of the incident energy, the photon energy into electricity. It means you have 150, if you have 1 kilowatt per square meter coming down, you have 150 watts per square meter electric peak. What happens with the rest? It is. Yeah, but it's nothing is disappearing in nature. It's hitting, and if 15% are electricity, what are the other photons doing? Heat it. Mm-hmm. That's true.
And reflection.
Yeah, but this is counted already in this efficiency. You know, one part is reflected. We count only what's coming in. So it's heat. Simply, it's heat. If you want to observe a large photovoltaic field, what you see is that hot air is lifting over it. And why I'm telling you this, because I want to make a strong point of a StirLing engine. If you cover the full house with photovoltaic panels, you will have a lot of electricity, but you will have much more hot air. And this hot air is just disappearing in the sky. If you have a StirLing engine, which is in the range of a photovoltaic module operating at this efficiency, it's different. Because, and as I said, you Olivier will go in more detail of StirLing, but I schematically show you again container filled with air in our case, and the top of it is suspended in a sort of a membrane, so it can move up and down. And we have inbuilt a heat exchanger through which it's a solar collector. Solar radiation is creating heat. This heat is going through in the heat exchanger, is exchanging the heat to the gas. So that's heated. And then we have on the other side, as we said, a heat exchanger which brings cooling, typically from the well, from the water. So we have here the high temperature, we have the low temperature. And inside we have sort of a piston which is going once in this position, once in this extreme position. Why? Because when it is in this position, all the air is at the hot side. We have the highest pressure. When it is in this position, all the air is exposed to the cold. So instead of bringing at one moment heat in and then cooling it from outside, we have installed permanently a cold loop and a hot loop, and the displacer is shifting from hot to cold, and this simply means that if we look on a pressure time scale, the moment we moving up here, the pressure is rising in the system because we heat the air, and the moment we are going back, pressure goes down and so on. We have because it looks like this in the real system, because we have a rotational system with flywheel and so on, and there are many other elements inside, like regenerators I don't describe now. But yes, it's a displacer brings the air once on to the cold side, or the air is faced with a heat exchanger which is cold, and in the other position all the air is exposed to the hot side. You know, at the beginning you would think you have a cylinder, and simple picture, you have a burner, biogas burner for example, and you heat the cylinder from outside. Then the pressure raises and your piston comes out, and over a flywheel system you change this into rotation. And now you have to go back, and if you don't have this configuration, now you need to cool from the outside the cylinder. If you have built in permanently the heating and the cooling, then you only must displace the gas from one side to the other to create this pressure fluctuation. And okay, why did I describe this? Because when we now said that the efficiency of such a system can be around 15% to 21% for the theoretical possible, then we are in the range of photovoltaics, but we are on the cool side. We can control the temperature of the cool side. We can go with this temperature higher than the temperature of the well, for example, to 40 degrees, because it's all the water we need for showering and for domestic use. Of course, in this moment, the efficiency will shrink to 13%, something like this, because we have reduced the delta T. But now we have instead from 100% of solar energy hit our collector. We have now 13% in electricity, but the rest at 40-degree hot water. So, of course, we always have losses by insulation, but in this case, the total efficiency, meaning exploiting the incoming energy stream, is not 13%, it's near 100%. That means an engine is not only producing mechanical power and via generator electricity, it's also producing the rejected heat. And this is a cogeneration between mechanical power and heat, so it's a big advantage.
I didn't get it. The last thing where you came to 100% this last step, I didn't get it.
Yeah.
And
If
you are speaking about the StirLing, you are not tracking the photovoltaic.
No, I take against a picture of the photovoltaic to explain it to you. In the case of the photovoltaics, 100%, in both cases 100% of solar energy hits our collector. And in photovoltaics, only 15% are usable as electricity. The other is warm air, which is not used. In the case of the StirLing engine, we have approximately the same efficiency for a low temperature StirLing engine in electricity, but the heat is concentrated in the warm water coming up. So, and this warm water is exactly the same amount of energy which was lifted out in the air. So in this case, the usable energy is nearly 100%.
Because you use the hot water for a shower.
Of course. And if you're going into, it's clear. Now we have to go to very...
But if you use the hot water for shower,
yeah.
then this means that be a more high temperature and the efficiency of the 30% will be lower.
Yes, no, I got from 50 to 13% already. Of course, if you would shower at 80 degrees, which is not good for your health, you will reduce it. No, this is such a mixture, just giving you the general difference between a thermodynamic conversion of energy in a low temperature StirLing, and again, low temperature is easy to achieve, compared to monoculture system creating only electricity. That's what I wanted to explain. express. So this is one of the advantages. Now you could say yes, but if you look to the large photovoltaic stations sitting in the country, in Germany you find huge of them. You go to Israel, in the desert you find huge megawatt and more stations. They cannot, there's nobody's living there. What should they do with the heat? They only need the electricity to put it in their grid, and the rest, okay. The rest is the rest, it's lost. But we are talking here about decentral, small, autonomous systems. And only there it makes sense. If I'm going in a big central power station, now coming back in principle, besides the photovoltaic, in our systems, in our modern systems, we have large coal power stations. We have gas turbines. And they produce also heat which could be used. But it's not economic to transport the heat in pipes from large distances in towns. But if you have it on a small size and sitting on your house roof or in your village, then you will need this heat. And if you are not doing it, if you wouldn't produce it like this, then you need extra equipment, extra solar collectors to produce all the heat you need. And one should never forget. Please.
I want to just a short comment. In Turkey, we are also using in small scale cogeneration.
Yeah.
In photovoltaics.
Yeah.
They're just making a little bit addition of by parts, a chilling system.
Yes.
And using the heat
Yes.
as a cogenerator, and
Yes.
it's also good for the efficiency of the photovoltaics.
Absolutely good.
And the efficiency decreases with the high temperatures. We are using it in small scale, but I'm not sure whether it's manufactured or not. But
It's a very good point, and everybody should cool photovoltaic cells actively to win the things. We worked a lot on this, and we have developed what we call cool photon filters in front of the PV panels to cool them. That's true. That's good. But so for StirLing, it's a given fact. We have a cogeneration fact. That's the one thing, and this alone, combined with the simplicity of the engine, you will see, is justifying that we answer the question why low temperature StirLing engines with a yes, we should have them because they are easy, they are simple, they use air, they don't need exotic gases, the temperatures involved are absolutely easily controllable. But now comes the next point, very important point.
There's a question before you go to the
Yeah, okay, go ahead. Ja.
Wenn wir so eine StirLing-Maschine haben, die jetzt gebaut haben, ne? Dann haben wir ja 500 bis 600 Kilogramm Stahl, wir haben Pipes, verschiedene Sachen. Wie lange muss so eine StirLing-Maschine laufen, damit sie überhaupt die Energie, die wir gebraucht haben, um das transportieren, wie weit kommt?
Okay, I will translate it. You know, it raises a very important question, and this is a question in technical terms called what is the gray energy? What is gray energy? Definition of gray energy of a system is the following. If you build a system, you need energy to build it. So if you have, and the question is raising is completely correct and good. If you need hundreds of kilograms of steel, you have to produce a steel in a forgery with 1,000 degrees centigrade. It requires energy and the piping and everything associated. So basically, the question is, how long must a system run to win back the energy which was put in to build it? That is the gray amortization. So it's clear, first of all, again, thank you, it's a very good question, that less material we have in, the less weight, the faster it will be. And you point out, these are heavy babies, so it will take time before they have their amortization. We calculated this for the engines we have at the moment. This is roughly 1 year. We have it back. But
How many hours working in 1 year?
if we work 24 hours, and I'm coming just to the next point, can we work 24 hours, 365 days? But I wanted to mention another point. There is a development in all these systems. And the development means that the status we have reached is for sure good to start going into applications, but we should not be completely satisfied about it. So what we are at the moment developing as the next generation of sun-powered StirLing engines, you would not recognize it. There's nearly no material at all. But that's future. So at the moment we are there. And now how can we reach that the engine runs 24 hours? That's another point. To repeat, application decentral, small, using both qualities I described here, electricity and heat. Now, we said small decentral systems, but we want that the systems become independent, autonomous. You can become only autonomous if you are 100% self-sufficient in energy. If not, if you say, okay, I am 70%, you will always depend from an outside energy input. So the interesting thing with solar energy is, especially if you go countries, Mali, every day we have so much more energy as ever we would need, but we have also nights in Mali. And if we need nighttime energy, it comes, what we said, to the problem of interim storage of the solar heat to use it driving the engine day and night. And this is exactly the strongest point of a low temperature StirLing engine. Because when you, what I mentioned, when you go to this very attractive 70% potential at 1000 degrees, of course you can store heat at 1000 degrees, but it becomes very technical. You need again, you can go with molten salts, not to 1000 degrees, up to 800 degrees, but then you have technological problems and so on. And if you are working at this temperature range, we simply apply, in the simplest case, hot water storage, which costs nearly nothing compared to the alternative, which is the photovoltaic electric storage. So if we add to this system, we go first from our collector, we heat our storage, well isolated tank, dimension in the way that we are collecting during daytime the energy to run the engine daytime and nighttime. So it will run 24 hours. And we compare this to the photovoltaic electric battery system. Again, I want to make a remark at the beginning, not to create the wrong impression. And I already said it, if you have your computer, I don't say you put a little heat storage and a little StirLing engine. It would be completely stupid. You put a lithium-ion battery in this case, and because the computers don't use a lot of energy, it's one of the charms. This is not energy production, this is information, and the transformation in the technical world of information dissipation in PC, semiconductors, electronic system is so that they need nearly no energy compared to your washing machine and to other things. So I'm a big fan of very small, high-tech electronic devices for communication running out of solar cells and of little batteries. But if we want to translate this to a household, and then typical American households, we have seen this. There's Elon Musk, I think I mentioned Elon Musk, you know. Everybody knows him?
We spoke about him yesterday.
Yeah, and everybody was here. So the Tesla man, he will be in 2022, he will deliver, that's the plan, photovoltaic areas with massive battery banks of lithium ion, and the costs per kilowatt hour of electricity, of course, must be competitive to the grid electricity, and only if you are competitive you will come into this market. So he predicts coming into the market in 2022, and the costs he predicts at the time 2022 of electricity is higher than today. That's what can be observed, and he says then we will have it. So there's a lot of assumptions inside. First he must build his really massive, huge, one of the largest factories in the world in Arizona. They just start building, and here comes again the questions of grey energy, because in order to produce lithium-ion batteries you need huge amounts of energy. So he was asked the question also, but from where do you, if you want now to bring to a country like USA the energy autonomy in the private homes through PV and batteries. What is your requirement of grey energy to produce it? So his answer was first looking fantastic, and secondly was not right. Because he said, okay, look, I have 10 hectares of surface on my factory roof. I put photovoltaic cells on it, and the energy of the photovoltaic cells will produce the energy to build the lithium-ion batteries. In principle, it's true, but only the power he wins from the surface of his roof is even not 1% of what he requires. So they will have to build a massive, huge, largest solar power station around. So going into these calculations, for the simple case of sunny countries, and I must remember that our impetus to develop these low temperature StirLing engines was sunny countries. It started in Mali when we studied the villages and in the surrounding countries. And there, under these conditions, you have statistically next day the sun comes up, you will have a maximum of 3-4 days of sandstorms. Sometimes that's what we studied. So we should extend our storage to such periods. And if we would come in a region in which it would be maybe 1 week or 14 days, then we should combine it with biogas typically. That's what we have learned, because biogas is a form of stored solar energy which is not losing like the temperature is losing in a sensible storage. And all these random conditions taken into account, we calculated it through for a 20 years lifetime cycle. That should be also always done. If you run 20-year system, we are compared to a photovoltaic battery system with such a, you could say, nearly primitive, simple solutions. Economically, we are about 4 to 5 times better. And the second thing, over the lifetime, yeah, because you have to rechange batteries, and in case of heat storage, you don't have to rechange. Then we have the other advantages I mentioned, that we don't need something exotic. We are not going to make the next, to impose the next political pressure onto countries like Bolivia having massive amounts of lithium. So the distribution, we are speaking this here as a peace center, and one of the major reasons of wars and struggle in the world is the fight for the energy reserves. Therefore, these are advantages. And the third one is, of course, it will be very difficult at the time being to install, for example, in Benin or in Mali or in Togo, a factory producing lithium-ion batteries. But it will be very simple to use the existing infrastructure of welders, of people working with metals to build those components. So that is the reason, the main reason we can become independent. Now, let's look a little bit more to the other possibilities associated to a low temperature StirLing engine. As you have seen yesterday, we can run the StirLing inversively, and then it's cooling. I think most of you could drink nice cold beer. We produce with it. And how does it function? It's
really quick too.
It's really quick too.
Yeah, it's efficient, very efficient. So one last little theoretical picture, so-called pressure volume diagram. It gives you the closed cycle, how such an engine works. If we introduce heat in the gas, the pressure is rising. So we need a crank system which allows that the highest pressure is reached before it's delivering through our mechanism this energy in motion. So when we have reached this point, and Olivier will explain this, then we are using the kinetic energy of the molecules to expand. Volume becomes larger, pressure becomes lower, until we have extracted the possible energy in the frame of this Carnot theorem. Then when we have reached this, here we're heating the gas, now we cool the gas, this side, and then we have to bring back the gas to the initial status. Therefore, we need a little bit energy which is coming out of the flywheel, recompressing it to the primary stage. And herein we have the energy of the system, and in the case of low temperature, we said we have the range 15% we can reach. If now someone turns on the flywheel and reversing the cycle runs this way. If you are running reversively by introducing mechanical energy to drive it, then we are creating temperature differences. Because we are not bringing in heat and cold. Now we are creating heat and cold. On the one side, it becomes cold. That's what we use for our cooling device here. And on the other side, we deliver heat. It's a heat pump. And since we reach a good portion of this theoretical efficiency thermodynamically, the same counts for the heat pump cooling cycle. The heat pump means the following. Everybody knows you put in your compressor some mechanical energy, and then you will have cooling. And you can have much more cooling energy than you put in mechanical energy, the heat pump effect. And the real stage we have reached today is that with a low temperature StirLing engine, if we bring in 1 unit of mechanical energy to drive it, we will have about 5 units of cooling. That means if we bring in, for example, in the SunPulse 500 watts of photovoltaic energy, we will have 2.5 kilowatts of ice producing cooler. That's calculated for a temperature difference between ice around 0 degree and the 25 degree water we start with. If you want to go much deeper, then it will become less than the multiplication factor of 5. If we want to cool only to the temperature of cold beer, 8 degrees, then it will be 7 like this. The theoretical possible is nearly double of this. So we have reached about 50% of the theoretical possible, which is not super exciting, but which is not bad. But it shows you the potential. In our next engine development, we call it pulsator, and I mentioned it, with very low masses, so direct energy will be 1 month maximum before we amortize as the cost of production. We will reach not 50% of the Carnot efficiency, but between 80 and 90%, nearly the ideal. And then it becomes even more attractive. We produce mechanical energy, electrical energy. The mechanical energy coming out of the engine will be used directly for milling, for tools, much more intelligent than putting electric motor between, which you would need if you produce only electricity. Heating, cooling, extending the operation over 24 hours. If coming into climatic conditions where the storage would become uneconomic for extreme situations, combine it with the heat which is available in place, which is storable. Biogas, or in the simplest case, a wood stove. If you have wood stoves and you run wood stoves in a cold climate, a lot of the energy is going out of the chimney, so you can use it here. And these are big advantages, because heat is available all over the places. Also think about existing structures with rejected heat from industrial processes. It's a huge potential. And I will end with this, with a statement from the year 1900. I think it was 32 or 33. The German industry, not having StirLing, they would have used it, but they built little steam engines to use all their rejected heat. So the German industry was completely autonomous in production of electricity because they closed the loop. Then came the Nazis and said, no, we need a centralization of the electric energy because they started to build the war machine and they needed to control this. And after Second World War, the law still existed, it's forbidden to use your rejected heat. Until my dear friend Hermann Scher, unfortunately passed way, very famous man, towards the alternative reasonable price for solar energy. He pointed this out to the Bundestag, so it became all right as a Nazi law, and from this time we started winning. So all this speaks in favor of a low temperature engine. However, what means low? Low, 100 degrees is a little bit cool for us. We can reach with vacuum collectors with wonderful efficiencies. So 200 degrees range with our fixed focus, we can easily reach with nearly optical efficiency 300 degrees. So of course the next things coming are, can we then, something for the free lab, can we go in the range of 200 degrees, we reach then 20 to 35% of mechanical efficiency, in principle easily feasible if we replace our membranes, which are at the moment at the limit of something like 200 degrees to membranes of 300 degrees. Firemen in the world are producing new textile structures, allowing them to go into fire of 500 degrees, so it's completely clear. At a given time, we may be in the efficiency range between 20 and 30% with these engines, but 13% are already working. Thank you very much. And
There are various estimates of how big a drain on the world's resources the digital economy is. One data pointer is that 1% of the world's carbon emissions are created by people just streaming video over their phones or on their PCs.
Smartphones, computers, data centers, and all the digital activities we take for granted are estimated to use around 7% of the world's electricity. And that's only going to get worse as we rely more and more on our devices.
Probably the best way to look at that is what's going on in data centers. These are these giant factories full of computers that are processing all of the information that you generate. These giant data centers are on a course to be using much more electricity by perhaps the end of the decade. Clearly that kind of a drain is just not sustainable. We need new solutions, we need novel solutions.
Scientists and startups around the world are developing low-energy computer chips, which could be better for the environment and upgrade the intelligence of our digital devices.
Everything's tied to computers getting better. It could be finance, it could be chemical engineering, name your field. So my goal since founding the company has been to develop a new computing paradigm, a new technology platform that will allow computers to continue to make progress.
It's not only about design, but also sending them for fabrication, testing them, and making system prototypes for various applications. The focus of the application would be reducing the energy consumption to the minimum level.
It's a very high risk, high reward type problem. So if we're successful, then we'll transform this industry. There'll be this enormous leap in this field.
From space hardware to toasters, almost everything in modern life depends on silicon-based semiconductors called chips. They're the things that make electronic items smart.
At a very fundamental level, semiconductors are made up of what's called transistors, and these are the absolutely microscopic digital switches, the on or offs. On or off means 1 or 0 in the digital realm. Say a modern graphics chip will have tens of billions of transistors on it, and this is something that's the size of your thumbnail. So how do we get all of these tiny switches onto something relatively small? Well, we do that by building up layers of material on a disk of silicon, scraping off patterns into those materials, layering on other materials until we have these tiny circuits that give the chip its function.
For half a century, the semiconductor industry has made chips exponentially faster and better by shrinking the size of transistors, turning room-sized computers into pocket-sized smartphones, propelling the digital revolution.
Clearly, new technology is presenting both management and staff with an ever-growing range of choices about how and where work will be done in the future.
But traditional computing is reaching its limit. State-of-the-art mass-produced chips are made with what's called 5-nanometer technology, a dimension that's smaller than a virus. And materials inside some devices are already 1 atom thick, meaning they can't be made any smaller.
We're reaching the limits of physics, we're reaching the limits of energy density. The increasing consensus in the chip industry is that these advances that we've got from silicon are beginning to come to an end. So that if we really want to take advantage of the full potential of artificial intelligence and the absolute ocean of data that we're all creating today, we're going to need new materials, we're going to need new programming models, we're going to need new versions of computers.
My personal first time about learning and discovering what a carbon nanotube was when I was just about finishing up college undergraduate, and I saw a presentation by the vice president of research of IBM. Immediately, I was thought it was very special. A carbon nanotube is a material made entirely of carbon atoms. The carbon atoms are arranged in a tube. Imagine taking a sheet of carbon atoms and rolling them into a tube, and then making that tube smaller and smaller and smaller and smaller until the diameter of that tube was just a few atoms. It's extremely small, which is about 100,000 times smaller than the diameter of an eyelash and 100 times smaller than a virus. The really cool thing about nanotubes is they conduct electricity better than just about any other material that's ever been discovered. Electrons will move along the length of a nanotube faster than they do in silicon. And that means you can get ultimately faster switching between on and off states. You can make faster computer chips. You can turn them on and off with less voltage. And that means they use less electricity, less power than silicon. In theory, nanotubes will be able to do 1,000 times better than silicon. Same computational capabilities, 1,000 times less power.
Another advantage is that carbon nanotubes can be processed at a low temperature, so layers of nanotubes can be built on top of one another. Silicon has to be processed at an extremely high temperature, which makes 3D layers much harder.
If you really think about a city, what happens when you run out of real estate in a city is you build skyscrapers, you build into the third dimension. And so if you can't make the transistors smaller, then you could improve your computer chip by making more transistors, by making multiple layers of transistors on top of other transistors.
Since the 1990s, when nanotubes were first invented in Japan, different methods have been developed to mass produce them. But every process creates two types of nanotubes, metallic ones and semiconducting ones.
A metallic nanotube, like a copper wire, it's stuck in the metallic state. You can't switch it. And that kills the circuits. So we need only semiconducting nanotubes to really make nanotube electronics work. So molecules and polymers that can be mixed in with the carbon nanotube powder, which is this tangled mess of nanotubes. And those molecules and polymers will stick to just the semiconducting ones and not the metallic ones, or they'll stick differently. And then you could sort the nanotubes and separate them based on these differences. Initially, in a powder, there's about 67% of the nanotubes are semiconducting. But using these chemical approaches, we could extract over 99.99% of the semiconducting nanotubes.
After the semiconducting nanotubes have been extracted, they float around in a solution. And so the next challenge is to line them up neatly on a silicon wafer, which can then be turned into a computer chip.
Carbon nanotubes really got me hooked and excited right from the beginning, and they really have the opportunity to potentially revolutionize electronics. This challenge of aligning them in these highly packed, highly aligned arrays has really been frustrating the field of carbon nanotube electronics since their discovery. During my PhD, I was kind of tasked with actually determining, how we can better align carbon nanotubes. We just found, kind of by accident, that when we layer carbon nanotube ink, or inks where carbon nanotubes are dissolved in solutions like organic solvents, if we layer that carbon nanotube ink on water, then instantaneously those carbon nanotubes will collect and confine at that ink-water interface, and that high ordering and induced ordering by themselves really helps to align the carbon nanotubes.
What you're seeing here is a aligned array of hundreds or thousands of carbon nanotubes. As you can see, individual nanotubes are these light-colored regions, and then the dark-colored region is the substrate. They're all really well aligned with respect to each other. Occasionally, there's a misaligned nanotube, and then we need to improve our manufacturing process to eliminate those instances.
The biggest current challenge is being able to achieve that high alignment and extremely uniform arrays across 300 millimeter wafers, which is an industry standard of silicon wafers, before they start changing silicon to integrate carbon nanotubes instead.
If we can overcome these challenges, if we can make these aligned nanotube wafers, major players in industry will really jump into this field, because just progress at that point can be very rapid.
The technique isn't perfect yet, but it's already an advance for carbon nanotube research. Michael and Catherine have founded a company with an aim to solve remaining challenges. But many more breakthroughs are needed 4 nanotube transistors have even the chance of replacing silicon.
It absolutely shows promise, but it's been showing promise for 20 years. There are many issues, how robust are these devices, but more importantly, can you manufacture them?
The semiconductor industry is based on silicon transistors, and enormous sums have already been invested in infrastructure to manufacture that technology. Plants have a price tag of $20 billion, take years to build, and need to be run for 24 hours a day to turn a profit. Change will be difficult, without a guarantee that carbon nanotubes will be cheaper.
Silicon's been around a long time. People know how to use it. They know how to program it. They know how to mass manufacture it. It's still, in terms of the economics, the winner. And until those economics change, nothing is going to replace it.
I've always been obsessed with computers. I had an opportunity to work in industry at a large semiconductor company for a number of years, and I got to see there some of the fundamental challenges associated with continuing to shrink transistors, and I found that to be not a very exciting future. So my goal with Light Matter since founding the company has been to develop a new computing paradigm, a new technology platform that allows you to do calculations using photonic devices.
Electronics uses electrons. That's the medium of transfer. That's what represents the data. Photonics is using photons, which is the basic constituency of light. So, for example, a fiber optic cable that spans the Pacific Ocean is using light to transmit information. Why is it using light? Well, it's because the energy required to shove electrons on a copper cable would be absolutely enormous, and you would just have too much signal decay. So, if you can convert that information into photons, you can send it faster and with less energy overhead. So that's obviously a desirable thing.
There's nothing faster than the speed of light. So when you think about the latency between when you make a query and when a photonic computer gives you an answer, it's really at the fundamental limit for how fast you can do these things. Electrical wires, there's a certain amount of time that it takes for them to turn on and off, and every time you do, it takes a lot of energy to do this, to turn this wire off and on. Now, with a photonic computer and photonics in general, you have a type of wire that doesn't take very long at all, femtoseconds, maybe even attoseconds to turn on. It takes almost no energy other than any light that's lost while the optical signal is propagating through that wire. You have another great property with photonics, which is that you can send multiple data streams through this photonic wire encoded in different colors or wavelengths, all at the same time. So you have massively parallel computation and communication through these nearly perfect wires.
The idea of silicon photonics has been around, again, for a long time. The problem comes with changing those electrons-based signals into photons. So the traditional way of doing that is to have all of these other pieces of equipment that are expensive and use lots of energy to do that. Silicon photonics is, well, maybe we can just design a chip that directly deals in both electrons and photons, that we can have, the benefits of both worlds. And that's what we're supposedly on the cusp of doing. Again, it's been promised for a long time. It's going to change the world, or has been about to change the world for a long time, and it hasn't yet.
But Light Matter still believes silicon photonics is going to happen, and it's harnessing existing laser technologies used in the telecoms and semiconductor processing industries. Their chips are specifically being made for AI applications like chatbots and self-driving cars. The startup plans to launch their first photonic computer later this year. One of their current products is an interconnect, which enables chips to talk to each other. It could help solve energy consumption issues in data centers and potentially bring down costs. In these huge factories, processors are closely arranged together so they can communicate at high speeds. But this also generates a massive amount of heat.
So not only do you have to put the power in to power all of these components, but then you have to use an enormous amount of power to actually cool them down, to stop them literally melting. What this company is trying to do is to come up with interconnects and ways of connecting components that use light rather than electrons over wires. So that means, in theory, that you could have a processor in one room, memory in another, storage in another, and that would help with the density and the power and the heat. And that's definitely a solution that's being tried by numerous companies, but we're still waiting for that to show, practical everyday results and be widely adopted.
Human brain is very efficient. Your brain operates all the time. It doesn't dissipate more than 10 to 20 watts, which is very small value, to solve the problem of Rubin cube. So the amount of energy which is required to learn and then operate is very low as compared to the actual system. Just solving the problem, put learning aside, that itself will need thousands of processors to become parallel and then dissipate a lot of power which can go beyond megawatt.
These scientists in India have been trying to build low-energy chips, mimicking the way the human brain works for years. The human brain is packed with neuron cells that communicate with each other through electrical pulses, known as spikes. Each neuron releases molecules that act as messengers and control if the electrical pulse is passed along the chain. This transmission happens in the gaps between neurons, which are called synapses.
Neurons and synapses, they are fundamentally different from the way computers compute. Computers use transistors, which are binary. They do 0, 1, on, off. The brain sort of does a similar thing, except that it works in analog. It's also partly stochastic. A neuron may spike or may not spike depending upon inherent internal randomness. The brain itself doesn't like to do repetitive things. It likes to do everything with slight variance. This sort of enables creativity. It sort of enables problem solving.
And the youngster's creative imagination is not neglected.
Once there was a bear that was twice the size of the earth and lived on the sun.
The connections are different. So if you look at a computer chip, every transistor roughly talks to about 10 transistors. Every neuron, on the other hand, talks to about 10,000 other neurons. And that's literally what makes it super parallel. Neurons use time as a token of information. Computers don't understand time per se. They just sort of work with digital numbers and do mathematical operations.
To mimic the architecture of our brain more closely, the team designed an artificial neural net based on the biological neural networks in our brain. Each artificial neuron is built with a few silicon transistors and connected to other neurons.
We try to mimic the auditory cortex. So the auditory cortex has these neurons which are connected in random. And that sounds weird, but it turns out it serves a very important function, which is in speech processing. What we are doing is that there are recurrent connections, which means that the neuron could go to any neuron, including itself, creating some sort of loopy pathways, which are fairly random. And these loops are part of the architecture. They are called liquid state machine. They naturally are able to process time series, like when you hear speech, which is sort of occurs in time. We are doing some analog compute. There is some noise also in the neurons, so there could be some stochasticity.
In the traditional or conventional computation platform, everything is digital. Everything is defined based on logic 1 and 0. Analog computers, which are eventually signals which can have any value, would be able to get more complexity, at the same time more functionality in the operation.
Here we have our neural network chip, which is on the test board. So what we'll do is we'll speak to the computer, and that will sort of convert the speech into spikes. It's going to get processed in the chip. We run the code. 1. So it detects a 1.
This neuromorphic chip has been able to recognize speech using a fraction of the energy used by a traditional chip. Just like biological neurons, the artificial neurons wait for inputs and only spike when data comes in, and that means lower energy consumption. Each neuron is also highly efficient by using a quantum mechanics phenomenon called band-to-band tunneling. So electrons are still able to pass through transistors with very low electric current.
Quantum tunneling is nothing that humans essentially have experience for. If you have a human being that has to cross over a hill, the human being has to walk up the hill, burn energy, and then walk down, which again burns energy. And so there is no way for you to cross this barrier without using energy. If you make this hill thinner and thinner, narrower and narrower, until it goes to the size scale on the order of, say, a few electron wavelengths, at which point an electron doesn't need to go above the barrier to surmount it. It can, in principle, tunnel through it, which means it will sort of disappear on one side and appear on the other side magically. If you take a transistor, there's the same idea that when it turns on, we have a barrier that we sort of reduce, and when we want to turn it off, we increase the barrier. That's when you expect no current to go through. But that is not true by quantum mechanics. So even through a barrier, when it's narrow enough, electrons can sort of quote-unquote tunnel through it.
So far, there are 36 artificial neurons on the chip, and their energy consumption is remarkably close to biological neurons.
If we want to approach the number of neurons which are already in the human brain, so we need billions of them. And therefore, we need to reduce the energy per spike generated by a single neuron as much as possible.
Intel, one of the world's biggest chip makers, has been working on brain-inspired chips for 7 years. They've released 2 versions of their neuromorphic research chip, Loihi. The latest one is only 32 square millimeters in size, but contains up to 1 million neurons. The company said Loihi has demonstrated multiple applications, including recognizing hazardous odors and enabling robotic arms to feel.
In the near term, based on the most recent results we've had with Loihi, I would say that solving optimization problems are the most exciting application. Things like planning, navigating. You can think of it as solving the shortest path in a map, for example, if you want to get from point A to point B. these kind of optimization problems are conventionally really compute heavy, but we found that on a neuromorphic architecture, we can reduce the computational demands by orders of magnitude. So over a 10 times speed up, as well as over 1,000 times energy reduction. Probably the majority of the groups that are working with Loihi sees robotics as kind of the long-term best application domain for neuromorphic chips. After all, brains evolved in nature to control bodies and to deal with real-world stimulus, respond to it in real time, and adapt to the unpredictable aspect of the real world. And if you think about robotics today, they perform very rigidly prescribed tasks. But if you want to deploy a robot into the real world, we really don't have the technology yet to make them as agile, as adaptive as we really would like. And so that's where we see neuromorphic chips really thriving.
Intel and its collaborators have used the Loihi chip to power iCub, a humanoid robot designed to learn in a way that children might.
This iCub robot is intended to interact with the environment as opposed to being pre-trained with static data sets beforehand. So using kind of saccadic motions, moving the eyeballs, it can trace through and detect change or edges in the objects in front of this robot. And using a fully neuromorphic paradigm, we're able to design a network that understands and learns new object classes, even at different angles and different poses. It adds to its understanding, its kind of dictionary of understand objects over time.
What is this called?
That's a mouse.
Oh, I see. This is a mouse. Let me have a look at that.
Sure. Can you show me the mouse?
Here is the mouse.
So far, all of this technology is at an early stage. But to fight climate change and power the progress of civilization, we need at least one of them to be a breakthrough.
Greener chips absolutely have to happen. People are concerned about the environmental impact. People are concerned about efficiency. People are concerned about the results and the way that chips can impact modern life. So there's been, an absolute blossoming of investment in chip startups and trying these things. This is definitely the time of great ideas. Will they all be successful? Absolutely not. But now I would say more than ever, there is a chance that out there, in some corner of the world, there is a chip startup that will be everywhere within maybe the next 10 years.
You can't get your enjoyment from only the successes in science. You need to get your enjoyment from just enjoying solving hard problems. And so if you fail, that is just part of the process of eventually finding a solution.
LEDs don't get their color from their plastic covers. And you can see that because here is a transparent LED that also glows the same red color. The color of the light comes from the electronics themselves. The casing just helps us tell different LEDs apart. In 1962, General Electric engineer Nick Holonyak created the first visible LED. It glowed a faint red. A few years after that, engineers at Monsanto created a green LED. But for decades, all we had were those two colors. So LEDs could only be used in things like indicators, calculators, and watches. If only we could make blue, then we could mix red, green, and blue to make white and every other color, unlocking LEDs for every type of lighting in the world, from light bulbs to phones to computers to TVs to billboards. But blue was almost impossible to make. Throughout the 1960s, every big electronics company in the world, from IBM to GE to Bell Labs, raced to create the blue LED. They knew it would be worth billions. Despite the efforts of thousands of researchers, nothing worked. 10 years after Holonyak's original LED turned into 20, then 30, and the hope of ever using LEDs for light faded away. According to a director at Monsanto, these won't ever replace the kitchen light. They'd only be used in appliances, car dashboards, and stereo sets to see if the stereo was on. This might still be true today, if not for one engineer who defied the entire industry and made 3 radical breakthroughs to create the world's first blue LED. Shuji Nakamura was a researcher at a small Japanese chemical company named Nishia. They had recently expanded into the production of semiconductors to be used in the manufacture of red and green LEDs. But by the late 1980s, the semiconductor division was on its last legs. They were competing against far more established companies in a crowded market, and they were losing. Tensions started to run high. Younger employees begged Nakamura to create new products, while senior workers called his research a waste of money. And at Nishia, money was in short supply. Nakamura's lab mainly consisted of machinery he had scavenged and welded together himself. Phosphorus leaks in his lab created so many explosions that his coworkers had stopped checking in on him. By 1988, Nakamura's supervisors were so disillusioned with his research that they told him to quit. So it was out of desperation that he brought a radical proposal to the company's founder and president, Nobuo Ogawa. The elusive blue LED that the likes of Sony, Toshiba, and Panasonic had all failed at. What if Nishida could be the one to create it? After suffering loss after loss on their semiconductors for more than a decade, Ogawa took a gamble. He devoted 500 million yen, or $3 million, likely around 15% of the company's annual profit, to Nakamura's moonshot project. Everyone knew that LEDs had the potential to replace light bulbs, because light bulbs, the universal symbol for a bright idea, are actually terrible at making light. They work by running current through a tungsten filament, which gets so hot it glows. But most of the electromagnetic radiation comes out as infrared heat. Only a negligible fraction is visible light. In contrast, LED stands for light-emitting diode. It's right there in the name. LEDs primarily create light, so they're far more efficient. And a diode is just a device with two electrodes, which only allows current to flow in one direction. So here's how an LED works. When you have an isolated atom, each electron in that atom occupies a discrete energy level. You can think of these energy levels like individual seats from a hockey stadium. And all atoms of the same element, when they are far apart from each other, have identical available energy levels. But when you bring multiple atoms together to form a solid, something interesting happens. The outermost electrons now feel the pull not only of their own nucleus, but of all the other nuclei as well. And as a result, their energy levels shift. So instead of being identical, they become a series of closely spaced but separate energy levels, an energy band. The highest energy band with electrons in it is known as the valence band, and the next higher energy band is called the conduction band. You can think of it like the balcony level. In conductors, the valence band is only partially filled. This means with a little bit of thermal energy, electrons can jump into nearby unfilled seats. And if an electric field is applied, they can jump from one unfilled seat to the next and conduct current through the material. In insulators, the valence band is full, and the difference in energy between the valence and conduction bands, the band gap, is large. So when an electric field is applied, no electrons can move. There are no available seats to move into in the valence band, and the band gap is too big for any electrons to jump into the conduction band. Which brings us to semiconductors. Semiconductors are similar to insulators, except the band gap is much smaller. This means at room temperature, a few electrons will have sufficient energy to jump into the conduction band, and now they can easily access nearby empty seats and conduct current. Not only that, the empty seats they left behind in the valence band can also move. Well, really, it's the nearby electrons jumping into those empty seats, but if you look from afar, it's as though the empty seat or hole is moving, like a positive charge, in the opposite direction to the electrons in the conduction band. By themselves, pure semiconductors are not that useful. To make them way more functional, you have to add impurity atoms into the lattice. This is known as doping. For example, in silicon, you can add a small number of phosphorus atoms. Phosphorus is similar to silicon, so it easily fits into the lattice, but it brings with it one extra valence electron. This electron exists in a donor level just beneath the conduction band. So with a bit of thermal energy, all these electrons can jump into the conduction band and conduct current. Since most of the charges that can move in this type of semiconductor are electrons, which are negative, this sort of semiconductor is called N-type, N for negative. But I should point out that the semiconductor itself is still neutral. It's just that most of the mobile charge carriers are negative. They are electrons. So there is also another type of semiconductor where most of the mobile charge carriers are positive, and it's called P-type. To make P-type silicon, you add a small number of atoms of, say, boron. Boron fits into the lattice, but brings with it one fewer valence electron than silicon, so it creates an empty acceptor level just above the valence band. And with a bit of thermal energy, electrons can jump out of the valence band, leaving behind holes. It is these positive holes which are mostly responsible for carrying current in the P-type semiconductor. Again, the material overall is uncharged, it's just that most of the mobile charge carriers are positive holes. Where things get interesting is when you put a piece of P-type and N-type together. Without even connecting this to a circuit, some electrons will diffuse from N to P and fall into the holes in the P-type. This makes the P-type a little negatively charged and the N-type a little positively charged. So there is now an electric field inside an inert piece of material. Electrons keep diffusing until the electric field becomes so large it prevents them from crossing over. And now we have established the depletion region, an area depleted of mobile charge carriers. There are no electrons in the conduction band and no holes in the valence band. If you connect a battery the wrong way to this diode, it simply expands the depletion region until its electric field perfectly opposes that of the battery, and no current flows. But if you flip the polarity of the battery, then the depletion region shrinks. The electric field decreases, and electrons can flow from N to P. When an electron falls from the conduction band into a hole in the valence band, that band gap energy can be emitted as a photon. The energy
chain to the electron is emitted as light, and this is how a light-emitting diode works. The size of the band gap determines the color of the light emitted. In pure silicon, the band gap is only 1.1 electron volts, so the photon released isn't visible, it's infrared light. These LEDs are actually used in remote controls like for your TV, and you can capture them on camera. Moving up the spectrum, you can see why the first visible light LEDs were red, and then green, and why blue was so hard. A photon of blue light requires more energy and therefore a larger band gap. By the 1980s, after hundreds of millions of dollars had been spent hunting for the right material, every electronics company had come up empty-handed. But researchers had at least figured out the first critical requirement: high-quality crystal. No matter what material you used for the blue LED, it required a near-perfect crystal structure. Any defects in the crystal lattice disrupt the flow of electrons, so instead of emitting their energy as visible light, it is instead dissipated as heat. So the first step in Nakamura's proposal to Ogawa was to disappear to Florida. He knew an old colleague there whose lab was beginning to use a new crystal-making technology called metal organic chemical vapor deposition, or MOCVD. An MOCVD reactor, essentially a giant oven, was and still is the best way to mass-produce clean crystal. It works by injecting vapor molecules of your crystal into a hot chamber, where they react with a base material called a substrate to form layers. It's important that the substrate lattice matches the crystal lattice being built on top of it to create a stable, smooth crystal. This is a precise art. The crystal layers often need to be as thin as just a couple of atoms. Nakamura joined the lab for a year to master MOCVD, but his time there was miserable. He wasn't allowed to use the working MOCVD, so he spent 10 of his 12 months assembling a new system almost from scratch. Even worse, his lab mates shunned him, because Nakamura didn't have a doctorate, nor any academic papers to his name, as Nishia didn't allow publishing. His lab mates, all PhD researchers, dismissed him as a lowly technician. This experience fueled him. Nakamura wrote, "I feel resentful when people look down on me. I developed more fighting spirit. I would not allow myself to be beaten by such people." He returned to Japan in 1989 with two things in hand. One, an order for a brand new MOCVD reactor for Nishia, and two, a fervent desire to get his PhD. At that time in Japan, you could earn a PhD without having to go to university, simply by publishing 5 papers. Nakamura had always known his chances of inventing the blue LED were low, but now he had a backup plan. Even if he didn't succeed, he could at least get his PhD. But now the question was, with MOCVD under his belt, which material should he research? By this time, scientists had narrowed the options down to 2 main candidates, zinc selenide and gallium nitride. These were both semiconductors with band gaps theoretically in the blue light range. Zinc selenide was the far more promising option. When grown in an MOCVD reactor, it had only a 0.3% lattice mismatch with its substrate, gallium arsenide. Therefore, zinc selenide crystal had about 1,000 defects per square centimeter, within the upper limit for LED functioning. Its only issue was that while scientists had figured out multiple different ways to create N-type zinc selenide, no one knew how to create P-type. In contrast, gallium nitride had been abandoned by almost everybody for 3 reasons. First, it was much harder to make a high-quality crystal. The best substrate for growing gallium nitride was sapphire, but its lattice mismatch was 16%. This resulted in higher defects, over 10 billion per square centimeter. The second problem was that, like zinc selenide, scientists had only ever created N-type gallium nitride using silicon. P-type was elusive. And third, to be commercially viable, a blue LED would have to have a total light output power of at least 1,000 microwatts. That's 2 orders of magnitude more than any prototype had ever achieved. So between the 2 candidates, almost all researchers were focused on zinc selenide. Nakamura surveyed the crowded field and decided that if he were going to publish 5 papers by himself, he'd better focus on gallium nitride, where the competition was much less fierce. This material's main claim to fame was one development back in 1972, when RCA engineer Herbert Maruska made a tiny gallium nitride blue LED, but it was dim and inefficient, so RCA slashed the project's budget, calling it a dead end. 20 years later, scientific opinion hadn't changed. When Nakamura attended the biggest applied physics conference in Japan, the talks on zinc selenide had over 500 attendees. The talks on gallium nitride had 5. 2 of those 5 attendees were the world experts on gallium nitride: Dr. Isamu Akazaki and his former grad student, Dr. Hiroshi Amano. In contrast to Nakamura's academic background, they were researchers at Nagoya University, one of Japan's best. A few years earlier, they had made a breakthrough on the first problem of high-quality crystal. Instead of growing gallium nitride directly on sapphire, they first grew a buffer layer of aluminum nitride. This has a lattice spacing in between that of the other 2 materials, making it easier to grow a clean gallium nitride crystal on top. The only issue was that the aluminum caused problems for the MOCVD reactor, making the process hard to scale. But Nakamura wasn't even close at this stage. Back at Nishia, he couldn't get gallium nitride to even grow normally in his new MOCVD reactor. After 6 months, desperate for results, he decided to take the machine apart and build a better version himself. His 10 months spent putting together a reactor in Florida were suddenly invaluable. He began following the same routine each day. Arrive at the lab at 7 a.m. Spend the first half of the day welding, cutting, and rewiring the reactor. Spend the rest of the day experimenting with the modified reactor to see what it can do. At 7 p.m., go home, eat dinner, wash, and sleep. Nakamura repeated this routine every single day, taking no weekends and no holidays except for New Year's Day, the most important holiday in Japan. After a year and a half of continuous work, he came into the lab on a winter day in late 1990. As usual, he tinkered around in the morning, grew a gallium nitride sample in the afternoon, and tested it. But this time, the electron mobility was 4 times higher than any gallium nitride ever grown directly on sapphire. Nakamura called it the most exciting day of his life. His trick was to add a second nozzle to the MOCVD reactor. The gallium nitride reactant gases had been rising in the hot chamber, mixing in the air to form a powdery waste. But the second nozzle released a downward stream of inert gas, pinning the first flow to the substrate to form a uniform crystal. For years, scientists had avoided adding a second stream to MOCVD because they thought it would only introduce more turbulence. But Nakamura used a special nozzle so that even when the streams combined, they remained laminar. He called his invention the two-flow reactor. Now he was ready to take on Akazaki and Amano, but instead of copying their aluminum nitride buffer layer, his two-flow design allowed him to make gallium nitride so smooth and stable, it itself could be used as a buffer layer on the sapphire substrate. This, in turn, yielded an even cleaner crystal of gallium nitride on top, without the issues of aluminum. Nakamura now had the highest quality gallium nitride crystals ever made, but just as he was getting started, things took a wrong turn. While he had been in Florida, Nobuo Ogawa had stepped back from Nishia to become chairman. In his day, Nobuo had been a risk-taking scientist, designing the company's first products. It's why he supported Nakamura's lofty plans all this time. But in his place, his son-in-law, Eiji Ogawa, became CEO of the company, and the younger Ogawa had a much stricter outlook. One Nishia client said, "He has a mind of steel, and he remembers everything." In 1990, an executive at Matsushita, an LED manufacturer and Nishia's biggest customer, visited the company to give a talk on blue LEDs. In it, he claimed zinc selenide was the way forward, declaring gallium nitride has no future. That very same day, Nakamura received a note from Eiji: "Stop work on gallium nitride immediately." Eiji had never supported the research and wanted to end what he saw as a colossal waste. But Nakamura crumpled up the note and threw it away. And he did so again and again when a succession of similar notes and phone calls came from company management. Out of spite, he published his work on the two-flow reactor without Nishia's knowledge. It was his first paper. 1 down, 4 to go. With crystal formation settled, he turned to the second obstacle, creating P-type gallium nitride. Here, Akazaki and Amano had again beaten him to the punch. They had created a gallium nitride sample doped with magnesium, but at first it didn't perform as a P-type as they expected. However, after exposing it to an electron beam, it did behave as a P-type, the world's first P-type gallium nitride after 20 years of trying. The catch was that no one knew why it worked, and the process of irradiating each crystal with electrons was too slow for commercial production. At first, Nakamura copied Akazaki and Amano's approach, but he suspected the beam of electrons was overkill. Maybe all the crystal needed was energy. So he tried heating magnesium-doped gallium nitride to 400 degrees Celsius in a process known as annealing. The result? A completely P-type sample. This worked even better than the shallow electron beam, which only made the surfaces of the samples P-type, and simply heating things up was a quick, scalable process. His work also revealed why the P-type had been so difficult. To make gallium nitride with MOCVD, you supply the nitrogen from ammonia, but ammonia also contains hydrogen. Where there should have been holes in the magnesium-doped gallium nitride, these hydrogen atoms were sneaking in and bonding with the magnesium, plugging all the holes. Adding energy to the system released the hydrogen from the material, freeing up the holes again. By now, Nakamura had all the ingredients to make a prototype blue LED, and he presented it at a workshop in St. Louis in 1992 and received a standing ovation. He was beginning to make a name for himself, but even though he had created the best prototype to date, it was more of a blue-violet color and still extremely inefficient, with a light output power of just 42 microwatts, well below the 1,000 microwatt threshold for practical use. At Nishia, the new CEO's patience had run out. Eiji sent written orders to Nakamura to stop tinkering and turn whatever he had into a product. His job was on the line. But in Nakamura's own words, I kept ignoring his order. I had been successful because I didn't listen to company orders and trusted my own judgment. At this point, he only had the third hurdle left, getting his blue LED to a light output power of 1,000 microwatts. A known trick to increase the efficiency of LEDs was to create a well, a thin layer of material at the PN junction called an active layer that shrinks the band gap just a bit. This encourages more electrons to fall from the N-type conduction band into holes in the P-type valence band. The best active layer for gallium nitride was already known to be indium gallium nitride, which would not only make the band gap easier to cross, but also narrow it just the right amount to bring its blue-violet gap down to true blue. This time, Akasaki and Amano didn't scoop Nakamura. They were stuck trying to grow indium gallium nitride in the first place. Amano recalled, it was generally said that gallium nitride and indium nitride would not mix, like water and oil. But Nakamura had an advantage, his ability to customize his MOCVD reactor. This allowed him to use brute force, adjusting the reactor to pump as much indium as he could onto the gallium nitride in the hopes that at least some would stick. To his surprise, the technique worked, giving him a clean indium gallium nitride crystal. He quickly incorporated this active layer into his LED, but the well worked a little too well and overflowed with electrons, leaking them back into the gallium nitride layers. Unfazed, within a few months, Nakamura had fixed this too, by creating the opposite of a well, a hill. He returned to his reactor one more time to make aluminum gallium nitride, a compound with a larger band gap that could block electrons from escaping the well once inside. The structure of the blue LED had become far more complex than anyone could have imagined, but it was complete. By 1992, Shuji Nakamura had this.
And I showed the gem. I told the gem come to my office. I showed the this great, and it's so hard. I have to have this, yeah.
After 30 years of searching by countless scientists, Nakamura had done it. He had created a glorious bright blue LED that could even be seen in daylight. It had a light output power of 1,500 microwatts and emitted a perfect blue at exactly 450 nanometers. It was over 100 times brighter than the previous pseudo-blue LEDs on the market. Nakamura wrote, I felt like I had reached the top of Mount Fuji. Nishia called a press conference in Tokyo to announce the world's first true blue LED. The electronics industry was stunned. A researcher from Toshiba remarked, everyone was caught with their pants down. The effect on Nishia's fortunes was immediate and explosive. Orders flooded in, and by the end of 1994, they were manufacturing 1 million blue LEDs per month. Within 3 years, the company's revenue had nearly doubled. In 1996, they made the jump from blue to white by placing a yellow phosphor over the LED. This chemical absorbs the blue photons and re-radiates them in a broad spectrum across the visible range. Soon enough, Nishia was selling the world's first white LED, at last unlocking the final frontier so many had doubted. LED lighting. Over the next 4 years, their sales doubled again. By 2001, their revenue was approaching $700 million a year. Over 60% came from blue LED products. Today, Nishia is one of the largest LED manufacturers in the world, with an annual revenue in the billions. As for Nakamura, to whom Nishia owed the quadrupling of its fortunes,
I increased my salary 60,000. Yeah.
I heard you only got a $170 bonus.
It's patent.
So you got a $170 bonus for the patent.
Yes.
This was all while the blue LED was generating hundreds of millions of dollars in sales. Eiji Ogawa had always seen Nakamura's stubborn individuality as a liability, not a strength. The message was clear. In 2000, after more than 20 years at Nishia, Nakamura left the company for the US, where job offers had been pouring in. But his troubles with Nishia weren't over. He began consulting for Cree, another LED company. Nishia was furious and sued him for leaking company secrets. Nakamura responded by countersuing Nishia for never properly compensating him for his invention, seeking $20 million. In 2001, the Japanese courts ruled with Nakamura and ordered Nishia to pay him 10 times his initial request. But Nishia appealed, and the case was eventually settled with a payout of $8 million. In the end, this was only enough to cover Nakamura's legal fees. This is all he got for an invention that now comprises an $80 billion industry. From house lights to street lights. While you watch this video on a phone If you're outside following traffic lights or displays, chances are you are relying on blue LEDs. We might even be getting too much of them. You may have heard warnings to avoid blue light from screens before bed because it can disrupt your circadian rhythm. That all comes from the gallium nitride blue LED. But as for lighting, there are virtually no downsides to an LED bulb. Compared to an incandescent or fluorescent bulb, they are far more efficient. They last many times longer, are safer to handle, and are completely customizable. 30 years after the first white LED, high-end bulbs today allow you to choose between 50,000 different shades of white. Most importantly, their price has come down to only a couple of dollars more than other types of bulbs, and at their efficiency, with average daily use and electricity pricing, you can recoup that cost in only 2 months and continue to save for years after that. The result is a lighting revolution. In 2010, just 1% of residential lighting sales in the world were LED. In 2022, it was over half. Experts estimate that within the next 10 years, nearly all lighting sales will be LED. The energy savings will be enormous. Lighting accounts for 5% of all carbon emissions. A full switch to LEDs could save an estimated 1.4 billion tons of CO2, equivalent to taking almost half the cars in the world off the road. Today, Nakamura's research is on the next generation of LEDs, micro LEDs and UV LEDs.
So what are they making in there? LED is a power device. This is among the best facility in the US. And this is because of you. What's a standard LED size?
300 times 200 microns.
Okay.
Smallest is 5 microns.
That is insanely tiny.
So basically you can use that for like VR displays, such as AR and VR.
You can have like a retina display that's like right up here.
Yep.
Human hair would be about that thick?
Yep.
And that's a really, really tiny LED.
UV LEDs could be used to sterilize surfaces, like in hospitals or kitchens. Just flick on the UV lights and pathogens would be dead in seconds.
COVID-19 UV LED companies are still pressing, but it's kind of good because everything's maybe using these UV LEDs. We can sterilize all the COVID-19
For anything there, we use indium gallium nitride. For UV, we use aluminum gallium nitride.
Okay.
The bandwidth is much bigger.
Do you think this is what's coming?
It's okay to work, but the problem is cost is still high. Since it's less than 10%, the cost is very high. If the efficiency become more than 50%, cost is almost comparable to the market now.
And you think it will happen, right? Like the efficiency will go up.
Yeah,
it's just a matter of time.
Yeah, I think so.
And he's even tackling one of the biggest challenges of our time.
I'm interested in physics.
Me too.
I'm still interested in nuclear fission, so recently I started the company of nuclear fission.
Really?
Oh yeah, last year.
No way!
No way, no.
In 2014, Nakamura, Akazaki, and Amano were awarded the Nobel Prize in Physics for creating the blue LED. Shortly afterwards, Nakamura publicly thanked Nishia for supporting his work, and he offered to visit and make amends, but they turned down his offer. And today, their relationship is still cold. But perhaps even more important than the Nobel Prize, by the time Nakamura released his blue LED in 1994, he had published over 15 papers, and he finally received his doctorate in engineering. Today, he has published over 900 papers. Throughout his entire journey, one thing has never changed. What is your favorite color?
Oh, blue.
Was it always blue, or only after you made the LED?
I was born the fishery village in front of the house is like ocean blue always.
While I was learning about Nakamura's story, I realized that what set him apart from the thousands of researchers trying to unlock the blue LED, it wasn't necessarily his knowledge, but his determination, critical thinking, and problem-solving skills. Where others saw dead ends, he saw potential solutions. So if you're looking for a free and easy way to start building these skills for yourself right now, look no further than today's sponsor, Brilliant. Brilliant will make you a better thinker and problem solver while helping you build real skills in everything from math and data science to programming, technology, and you name it. On Brilliant, you'll learn through discovery by trying things for yourself. And you'll not only gain knowledge of key concepts, but learn to apply them to real-world situations, all while building your intuition, giving you the tools to solve whatever problems come your way. There is so much to learn on Brilliant. They have thousands of interactive lessons on just about anything that you're curious about. And because each lesson is bite-sized, you can do them in just minutes. So if you're like me and made a resolution to learn something new every day this year, Brilliant will help you actually do it. The best part is you can learn from anywhere, right on your phone. So whenever you have a few minutes, you can be building a quicker, sharper mind. So to try everything Brilliant has to offer for free for 30 days, visit brilliant.org/Veritasium or click that link down in the description. And the first 200 of you will get 20% off Brilliant's annual premium subscription. So I want to thank Brilliant for sponsoring this video, and I want to thank you for watching. This is a video about one of the most important yet least understood understood concepts in all of physics. It governs everything from molecular collisions to humongous storms, from the beginning of the universe through its entire evolution to its inevitable end. It may in fact determine the direction of time and even be the reason that life exists. To see the confusion around this topic, you need ask only one simple question. What does the Earth get from the Sun?
What does the Earth get from Sun?
Well, it's light rays.
What do we get from the
Heat.
Sun?
Warmth.
Light. Vitamin D. We get vitamin D from
Do you get vitamin D from the ultraviolet rays?
Well, a lot of energy. What does the Earth get? Energy?
Yes, energy.
Energy.
Nailed it. Every day the Earth gets a certain amount of energy from the Sun, and then how much energy does the Earth radiate back into space relative to that amount that it gets from the Sun?
Probably not as much. I don't believe that it's just radiating right back.
I'd say less.
Less.
I'd say less.
I guess about 70%.
I think it's a fraction.
I'd say 20%.
Because we use some of it.
We use some of the energy.
We consume a lot, right?
But the thing about energy is it never really goes away. You can't really use it up.
It would have to break even, wouldn't it? Same amount, yeah.
Cause and effect, it'd be equal in some ways, right?
For most of the Earth's history, it should be exactly the same amount of energy in from the Sun as Earth radiates into space.
Wow.
Because if we didn't do that, then the Earth would get a lot hotter. That'd be a problem.
That'd be a big problem.
So if that is the case,
Yeah.
then what are we really getting from the Sun?
That's a good question. It gives us a nice tan.
It gives us a nice tan. I love it. We're getting something special from the Sun.
I don't know. What do we get without the energy?
But nobody talks about it. To answer that, we have to go back to a discovery made 2 centuries ago. In the winter of 1813, France was being invaded by the armies of Austria, Prussia, and Russia. The son of one of Napoleon's generals was Sadi Carnot, a 17-year-old student. On December 29th, he writes a letter to Napoleon to request to join in the fight. Napoleon, preoccupied in battle, never replies. But Carnot gets his wish a few months later when Paris is attacked. The students defend a chateau just east of the city, but they're no match for the advancing armies, and Paris falls after only a day of fighting. Forced to retreat, Carnot is devastated. 7 years later, he goes to visit his father, who's fled to Prussia after Napoleon's downfall. His father was not only a general, but also a physicist. He wrote an essay on how energy is most efficiently transferred in mechanical systems. When his son comes to visit, they talk at length about the big breakthrough of the time, steam engines. Steam engines were already being used to power ships, mine ore, and excavate ports. And it was clear that the future industrial and military might of nations depended on having the best steam engines. But French designs were falling behind those of other countries, like Britain, so Sadi Carnot took it upon himself to figure out why. At the time, even the best steam engines only converted around 3% of thermal energy into useful mechanical work. If he could improve on that, he could give France a huge advantage and restore its place in the world. So he spends the next 3 years studying heat engines. And one of his key insights involves how an ideal heat engine would work, one with no friction and no losses to the environment. It looks something like this. Take 2 really big metal bars, one hot and one cold. The engine consists of a chamber filled with air, where heat can only flow in or out through the bottom. Inside the chamber is a piston, which is connected to a flywheel. The air starts at a temperature just below that of the hot bar. So first the hot bar is brought into contact with the chamber. The air inside expands with heat flowing into it to maintain its temperature. This pushes the piston up, turning the flywheel. Next, the hot bar is removed, but the air in the chamber continues to expand, except now, without heat entering, the temperature decreases, in the ideal case, until it is the temperature of the cold bar. The cold bar is brought into contact with the chamber, and the flywheel pushes the piston down, and as the air is compressed, heat is transferred into the cold bar. The cold bar is removed, the flywheel compresses the gas further, increasing its temperature until it is just below that of the hot bar. Then the hot bar is connected again, and the cycle repeats. Through this process, heat from the hot bar is converted into the energy of the flywheel. And what's interesting to note about Carnot's ideal engine is that it is completely reversible. If you ran the engine in reverse, first the air expands, lowering the temperature, then the chamber is brought into contact with the cold bar, the air expands more, drawing in heat from the cold bar. Next, the air is compressed, increasing its temperature. The chamber is placed on top of the hot bar, and the energy of the flywheel is used to return the heat back into the hot bar. However many cycles were run in the forward direction, you could run the same number in reverse, and at the end, everything would return to its original state, with no additional input of energy required. So by running an ideal engine, nothing really changes you can always undo what you did. So what is the efficiency of this engine? Since it's fully reversible, you might expect the efficiency to be 100%, but that is not the case. Each cycle, the energy of the flywheel increases by the amount of heat flowing into the chamber from the hot bar minus the heat flowing out of the chamber at the cold bar. So to calculate the efficiency, we divide this energy by the heat input from the hot bar. Now the heat in on the hot side is equal to the work done by the gas on the piston, and this will always be greater than the work done by the piston on the gas on the cold side, which equals the heat out. And this is because on the hot side, the hot gas exerts a greater pressure on the piston than that same gas when cold. To increase the efficiency of the engine, you could increase the temperature of the hot side, or decrease the temperature of the cold side, or both. Lord Kelvin learns of Carnot's ideal heat engine and realizes it could form the basis for an absolute temperature scale. Imagine that the gas is allowed to expand an extreme amount, so much that it cools to the point where all the gas particles effectively stop moving. Then they would exert no pressure on the piston, and it would take no work to compress it on the cold side, so no heat would be lost. This is the idea of absolute zero, and it would make for a 100% efficient engine. Using this absolute temperature scale, the Kelvin scale, we can replace the amount of heat in and out with the temperature of the hot and cold side respectively, because they are directly proportional. So we can express efficiency like this, which we can rewrite like this. What we have learned is that the efficiency of an ideal heat engine doesn't depend on the materials or the design of the engine, but fundamentally on the temperatures of the hot and cold sides. To reach 100% efficiency, you need infinite temperature on the hot side or absolute zero on the cold side, both of which are impossible in practice. So even with no friction or losses to the environment, it's impossible to make a heat engine 100% efficient. And that's because to return the piston to its original position, you need to dump heat into the cold bar, so not all the energy stays in the flywheel. Now, in Carnot's time, high-pressure steam engines could only reach temperatures up to 160 degrees Celsius, so their theoretical maximum efficiency was 32%, but their real efficiency was more like 3%. That's because real engines experience friction, dissipate heat to the environment, and they don't transfer heat at constant temperatures. So for just as much heat going in, less energy ends up in the flywheel. The rest is spread out over the walls of the cylinder, the axle of the flywheel, and is radiated out into the environment. When energy spreads out like this, it is impossible to get it back. So this process is irreversible. The total amount of energy didn't change, but it became less usable. Energy is most usable when it is concentrated, and less usable when it's spread out. Decades later, German physicist Rudolf Clausius studies Carnot's engine, and he comes up with a way to measure how spread out the energy is. He calls this quantity entropy. When all the energy is concentrated in the hot bar, that is low entropy. But as the energy spreads to the surroundings, the walls of the chamber and the axle, well, entropy increases. This means the same amount of energy is present, but in this more dispersed form, it is less available to do work. In 1865, Clausius summarizes the first two laws of thermodynamics like this. First, the energy of the universe is constant. And second, the entropy of the universe tends to a maximum. In other words, energy spreads out over time. The second law is core to so many phenomena in the world. It's why hot things cool down and cool things heat up, why gas expands to fill a container, why you can't have a perpetual motion machine, because the amount of usable energy in a closed system is always decreasing. The most common way to describe entropy is as disorder, which makes sense because it is associated with things becoming more mixed, random, and less ordered. But I think the best way to think about entropy is as the tendency of energy to spread out. So why does energy spread out over time? I mean, most of the laws of physics work exactly the same way, forwards or backwards in time. So how does this clear time dependence arise? Well, let's consider two small metal bars, one hot and one cold. For this simple model, we'll consider only 8 atoms per bar. Each atom vibrates according to the number of energy packets it has. The more packets, the more it vibrates. So let's start with 7 packets of energy in the left bar and 3 in the right. The number of energy packets in each bar is what we'll call a state. First, let's consider just the left bar. It has 7 energy packets which are free to move around the lattice. This happens non-stop. The energy packets hop randomly from atom to atom, giving different configurations of energy. But the total energy stays the same the whole time. Now let's bring the cold bar back in with only 3 packets and touch them together. The energy packets can now hop around between both bars, creating different configurations. Each unique configuration is equally likely. So what happens if we take a snapshot at one instant in time and see where all the energy packets are? So stop. Look at this. Now there are 9 energy packets in the left bar and only 1 in the right bar. So heat has flowed from cold to hot. Shouldn't that be impossible because it decreases entropy? Well, this is where Ludwig Boltzmann made an important insight. Heat flowing from cold to hot is not impossible, it's just improbable. There are 91,520 configurations with 9 energy packets in the left bar, but 627,264 with 5 energy packets in each bar. That is, the energy is more than 6 times as likely to be evenly spread between the bars. But if you add up all the possibilities, you find there's still a 10.5% chance that the left bar ends up with more energy packets than it started. So why don't we observe this happening around us? Well, watch what happens as we increase the number of atoms to 80 per bar, and the energy packets to 100, with 70 in the left bar and 30 in the right. There is now only a 0.05% chance that the left solid ends up hotter than it started. And this trend continues as we keep scaling up the system. In everyday solids, there are around 100 trillion atoms, and even more energy packets. So heat flowing from cold to hot is just so unlikely that it never happens. Think of it like this Rubik's Cube. Right now, it is completely solved. But I'm going to close my eyes and make some turns at random. If I keep doing this, it will get further and further from being solved. But how can I be confident that I'm really messing this cube up? Well, because there's only one way for it to be solved, a few ways for it to be almost solved, and quintillions of ways for it to be almost entirely random. Without thought and effort, every turn moves the Rubik's Cube from a highly unlikely state, that of it being solved, to a more likely state, a total mess. So if the natural tendency of energy is to spread out and for things to get messier, then how is it possible to have something like air conditioning, where the cold interior of a house gets cooler and the hot exterior gets hotter? Energy is going from cold to hot, decreasing the entropy of the house. Well, this decrease in entropy is only possible by increasing the entropy a greater amount somewhere else. In this case, at a power plant, the concentrated chemical energy in coal is being released, heating up the power plant and its environment, spreading to the turbine, the electric generators, heating the wires all the way to the house, and producing waste heat in the fans and compressor. Whatever decrease in entropy is achieved at the house is more than paid for by an increase in entropy required to make that happen. But if total entropy is constantly increasing, and anything we do only accelerates that increase, then how is there any structure left on Earth? How are there hot parts separate from cold parts? How does life exist? Well, if the Earth were a closed system, the energy would spread out completely, meaning all life would cease, everything would decay and mix, and eventually reach the same temperature. But luckily, Earth is not a closed system, because we have the sun. What the sun really gives us is a steady stream of low entropy, that is concentrated, bundled up energy. The energy that we get from the sun is more useful than the energy we get back. It's more compact, it's more clumped together. Plants capture this energy and use it to grow and create sugars. Then animals eat plants and use that energy to maintain their bodies and move around. Bigger animals get their energy by eating smaller animals, and so on. And each step of the way, the energy becomes more spread out.
Okay, interesting.
Yeah.
Oh wow, I did not know that.
There you go. Ultimately, all the energy that reaches Earth from the sun is converted into thermal energy, and then it's radiated back into space. But in fact, it's the same amount. I know this is.
You do know this is.
I'm a PhD physicist.
Okay.
The increase in entropy can be seen in the relative number of photons arriving at and leaving the Earth. For each photon received from the sun, 20 photons are emitted. And everything that happens on Earth, plants growing, trees falling, birds stampeding, hurricanes and tornadoes, people eating, sleeping, and breathing, all of it happens in the process of converting fewer, higher energy photons into 20 times as many lower energy photons. Without a source of concentrated energy and a way to discard the spread out energy, life on Earth would not be possible. It has even been suggested that life itself may be a consequence of the second law of thermodynamics. If the universe tends toward maximum entropy, then life offers a way to accelerate that natural tendency, because life is spectacularly good at converting low entropy into high entropy. For example, the surface layer of seawater produces between 30 to 680% more entropy when cyanobacteria and other organic matter is present than when it's not. Jeremy England takes this one step further. he's proposed that if there is a constant stream of clumped up energy, this could favor structures that dissipate that energy. And over time, this results in better and better energy dissipators, eventually resulting in life. Or, in his own words, you start with a random clump of atoms, and if you shine light on it for long enough, it should not be so surprising that you get a plant. So life on Earth survives on the low entropy from the sun. But then, where did the sun get its low entropy? The answer is the universe. If we know that the total entropy of the universe is increasing with time, then it was lower entropy yesterday, and even lower entropy the day before that, and so on all the way back to the Big Bang. So right after the Big Bang, that is when the entropy was lowest. This is known as the past hypothesis. It doesn't explain why the entropy was low, just that it must have been that way for the universe to unfold as it has. But the early universe was hot, dense, and almost completely uniform. I mean, everything was mixed, and the temperature was basically the same everywhere, varying by at most 0.001%. So how is this low entropy? Well, the thing we've left out is gravity. Gravity tends to clump matter together. So taking gravity into account, having matter all spread out like this would be an extremely unlikely state. And that is why it's low entropy. Over time, as the universe expanded and cooled, matter started to clump together in more dense regions. And in doing so, enormous amounts of potential energy were turned into kinetic energy. And this energy could also be used, like how water flowing downhill can power a turbine. But as bits of matter started hitting each other, some of their kinetic energy was converted into heat. So the amount of useful energy decreased, thereby increasing entropy. Over time, the useful energy was used. In doing so, stars, planets, galaxies, and life were formed, increasing entropy all along. The universe started with around 10 to the 88 Boltzmann constants worth of entropy. Nowadays, all the stars in the observable universe have about 9.5 times 10 to the 80. The interstellar and intergalactic medium combined have almost 10 times more, but still only a fraction of the early universe. A lot more is contained in neutrinos and in photons of the cosmic microwave background. In 1972, Jacob Bekenstein proposed another source of entropy: black holes. He suggested that the entropy of a black hole should be proportional to its surface area. So as a black hole grows, its entropy increases. Famous physicists thought the idea was nonsense, and for good reason. According to classical thermodynamics, if black holes have entropy, then they should also have a temperature. But if they have temperatures, they should emit radiation and not be black after all. The person who set out to prove Bekenstein wrong was Stephen Hawking. But to his surprise, his results showed that black holes do emit radiation, now known as Hawking radiation, and they do have a temperature. The black hole at the center of the Milky Way has a temperature of about 100 trillionth of a Kelvin, emitting radiation that is far too weak to detect, so still pretty black. But Hawking confirmed that black holes have entropy, and Bekenstein was right. Hawking was able to refine Bekenstein's proposal and determine just how much entropy they have. The supermassive black hole at the center of the Milky Way has about 10 to the 91 Boltzmann constants of entropy. That is 1,000 times as much as the early observable universe, and 10 times more than all the other particles combined. And that is just one black hole. All black holes together account for 3 times 10 to the 104 Boltzmann constants worth of entropy. So almost all the entropy of the universe is tied up in black holes. That means the early universe only had about 0.00000000003% of the entropy it has now. So the entropy was low, and everything that happens in the universe, like planetary systems forming, galaxies merging, asteroids crashing, stars dying, to life itself flourishing, all of that can happen because the entropy of the universe was low, and it has been increasing. And it all happens only in one direction. We never see an asteroid uncrash, or a planetary system unmix into the cloud of dust and gas that made it up. There is a clear difference between going to the past and the future, and that difference comes from entropy. The fact that we are going from unlikely to more likely states is why there is an arrow of time. This is expected to continue until, eventually, the energy gets spread out so completely that nothing interesting will ever happen again. This is the heat death of the universe. In the distant future, more than 10 to the 100 years from now, after the last black hole has evaporated, the universe will be in its most probable state. Now, even on large scales, you would not be able to tell the difference between time moving forwards or backwards, and the arrow of time itself would disappear. So it sounds like entropy is this awful thing that leads us inevitably towards the dullest outcome imaginable. But just because maximum entropy has low complexity does not mean that low entropy has maximum complexity. It's actually more like this tea and milk. I mean, holding it like this is not very interesting. But as I pour the milk in, the two start to mix, and these beautiful patterns emerge. They arise in an instant, and before you know it, they're gone, back to being featureless. Both low and high entropy are low in complexity. It's in the middle where complex structures appear and thrive. And since that's where we find ourselves, let's make use of the low entropy we've got while we can. With the right tools, we can understand just about anything, from a cup of tea cooling down to the evolution of the entire universe. And if you're looking for a free and easy way to add powerful tools to your arsenal, then you should check out this video's sponsor, Brilliant.org. With Brilliant, you can master key concepts in everything from math and data science to programming and physics. All you need to do is set your goal, and Brilliant will design the perfect learning path for you, equipping you with all the tools you need to reach it. Want to learn how to think like a programmer? Then Brilliant's latest course, Thinking in Code, is a fast and easy way to get there. Using an intuitive drag-and-drop editor, it teaches you what you really need to know, including essential concepts like nesting and conditionals. You can start by jumping right in to program a robot, and then learn how to apply your new tools to your everyday life, like automating reminders on your phone or building a bot that filters your matches on a dating app. What I love about Brilliant is that they connect what you learn to real-world examples. And because each lesson is hands-on, you'll build real intuition. So you can put what you've learned to good use. To try everything Brilliant has to offer free for a full 30 days, visit brilliant.org/Veritasium. I will put that link down in the description. And through that link, the first 200 of you to sign up will get 20% off Brilliant's annual premium subscription. So I want to thank Brilliant for sponsoring this video, and I want to thank you for watching. Here's what happens when you put your DNA under a microscope.
You can extract some from your mouth, just gargle salt water, and mix this with soap and rubbing alcohol. You'll get a gooey mass at the top. This is DNA. Most of it is yours, but some of it actually comes from bacteria living in your mouth. At 100 times magnification, you'll see these strings, which are coiled up DNA, proteins, and debris all clumped together. But looking at them is pretty much useless.
I mean, even with $1 million electron microscope, you can't actually see the genetic code that makes you you. So how do you read DNA?
DNA evidence.
DNA. Your family secrets. You are not the problem. Diseases you haven't been diagnosed with yet.
Predicting or even diagnosing cancers.
The tiny quirks of what makes you you. But for the vast majority of human history, we have not been able to read it. It is completely illegible.
All of this might still be impossible today, if not for one man who took a lot of drugs and stumbled upon a discovery that unlocked DNA forever. Also, he was kind of a jerk.
In the 1960s, as a biochemistry student at Berkeley, Kary Mullis wasn't interested in going to his classes. He was too busy taking LSD, and lots of it. Mullis didn't take university very seriously. His PhD dissertation was filled with jokes, and the committee refused to approve it until he, quote, cut all the wacko stuff out. But LSD fueled his eccentric genius, sparking all sorts of interesting